Okay, I want us to look at the same problem and solve it using a different coordinate system. This problem is a nice problem to practice because there are several different places that might make sense to put your origin. So in the previous version, we put the origin on the left side of the rod. What I'm going to do now is I'm going to choose the right side of the rod as my origin. So I'm going to go ahead and put the y-axis right here. So that places my origin at the right end of the rod. And I'll go ahead and have positive x to the left, positive y upward. And that'll be my sign convention for the problem. So that's a full coordinate system. The choice of an origin and the choice of a sign convention is what you need there. So I can leave my dq and dx and stuff from the other diagram, my de. I'm going to draw in where my x would be, right? Always from the origin to your differential element. So here's x. And of course, that's positive x since x is positive to the left. All right. So what we're starting with again is that the electric field due to a point charge is kq over r squared. We're writing that in differential form. K dq over r squared. And that's the expression that we're going to integrate. So we need to then define dq. So this is a linear charge again. So it is a good practical choice for me to define it as lambda dx. Remember that it's okay if we don't know lambda. In this problem, we're given that the overall charge of the rod is negative lowercase x, and we know the length of the rod, so we can fully define lambda in our case. So let's now define r. And I can look at my diagram and let's be sure and label r. So let's do that. So r, remember, is what locates our differential element. So we're coming like from here to our point of interest. So this distance in here is r. So x locates differential element with respect to coordinate system, and r locates the differential element with respect to the point of interest. And you need to link them as you write one in terms of the other. So when we define r, we define it in terms of x. And if you label stuff in your diagram, it really helps you see. Like if you look at my diagram right now, it's really obvious what r is equal to for this problem, and it's going to be equal to x plus a. Okay. So then I can write my, and is there any cancellation? Let's pause and think about that. Right, surviving component, is there any cancellation? No, we don't have any cancellation, just for the same reason that we had last time. So I can write my DE. My DE would be equal to K times DQ, which is going to be lambda dx, over r squared, which in this case is x plus a squared. So that should give me a pretty simple integral there. I would get then E is equal to K lambda dx. The K and lambda could be pulled out front there, over a plus x squared quantity squared. And when I look at my limits there, now look up, remember that we are writing this in terms of x. So where do we start summing? Where do we stop summing? So we start summing at x equals 0. We stop summing at x equal L for this particular choice. And yeah, I can go back and write that lambda in terms of my charge Q and L. We could do that. So that would end up being K, Q over L. All those would be constant, right? outside of dx over a plus x, or x plus a, doesn't matter, squared. And that would be 0 to L.